Hello everyone, good evening. So here we shall solve some KCET previous year questions on the chapter dual nature of matter and radiation. So any doubts if you have, then please write us in the comment section. And in any other chapter of physics, if you feel more difficulty, then please mention the name of that chapter also in the comment section. Then we shall give more priority on it and solve more and more questions on that chapter. Also, some important homework questions on every chapter will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link has been provided in the description. Here we shall start from the very first question onwards. It's told that when a piece of metal is illuminated by a monochromatic light of wavelength lambda, its stopping potential is 3 Vs. When same surface is illuminated by light of wavelength 2 lambda, then stopping potential becomes Vs. The value of the threshold wavelength for photoelectric emission will be. So when metal is illuminated by a wavelength lambda, then the stopping potential is 3 Vs. So I can say that 3 Vs, that is equal to hc by lambda minus hc by lambda naught, where lambda naught is the threshold wavelength for photoelectric emission. Threshold wavelength for photoelectric emission. So this lambda naught we have to find. And the same surface is illuminated by light of wavelength 2 lambda, then the stopping potential is Vs. So Vs is equal to hc by 2 lambda minus hc by lambda naught. So therefore I can write that 3 times this hc by 2 lambda minus hc by lambda naught, that is equals to hc by lambda minus hc by lambda naught. So hc will cancel out, then we can write it as 3 by 2 lambda minus 3 by lambda naught, that is equal to 1 by lambda minus 1 by lambda. So this will be equal to 3 by lambda naught minus 1 by lambda naught, that is equal to 3 by 2 lambda minus 1 by lambda. So therefore I can write this as 2 by lambda naught, that is equals to, I can write 2 by 2 lambda, which is 1 by 2 lambda. Therefore lambda naught, that is equals to 4 lambda. So option C is the correct answer. Therefore the threshold wavelength is 4 lambda. Then in question number 2 it is told the maximum kinetic energy of emitted electrons in a photoelectric emission does not depend on the maximum kinetic energy, that is equals to h nu minus h nu naught. So h nu naught, this is called the work function. It is called, it is represented by phi naught, work function. So the maximum kinetic energy of the emitted electrons, it depends on work function, does not depend on intensity wavelength. Yeah, so it does not depend on the intensity. Option A is the correct answer. Question number 3 it is told if an electron and a proton have the same de Broglie wavelength, an electron and a proton have the same de Broglie wavelength, their lambda is the same, then the kinetic energy of the electron is, we can say lambda is equal to h by p, and p square by 2m, that is equals to kinetic energy. Therefore I can say p is equals to square root of 2m into kinetic energy. So therefore I can say lambda, that is equals to h by square root of 2 into mass of electron into kinetic energy of the electron. That is also equal to h by square root of 2 into mass of the proton into kinetic energy of the proton. Then h and h will cancel out, 2 and 2 also will cancel. Then if we square both sides, then we will get that me into ke, that is equal to mp into kp. Therefore, the kinetic energy of the electron, that is equal to mass of the proton by mass of the electron into the kinetic energy of the proton. So now mass of proton is much higher than mass of the electron. So I can say kinetic energy of the electron is much greater than kinetic energy of the proton. So option A is the correct answer. The kinetic energy of an electron gets tripled, then the de Broglie wavelength associated with it changes by a factor. The de Broglie wavelength of the de Broglie wavelength of an electron is given as h by square root of 2m into k, where m is the mass of the electron and k is the kinetic energy of the electron. So now if the kinetic energy increases to 3 times, then the wavelength also will change to 1 by root 3 times of the wavelength. Since why if kinetic energy, if the new kinetic energy is 3k, then the new de Broglie wavelength, that will be lambda dash, that is h by root over 2m into 3k, that is equal to 1 by root 3 into h by root over 2mk, is equal to lambda by root 3. So the wavelength changes by a factor 1 by root 3. Option C is the correct answer. And in question number 5, it told that G.P. Thomson experimentally confirmed the existence of matter waves by the phenomena of diffraction. Since he used the electron and showed that electrons can behave as waves, which are called as the electron. So the electron waves can show the phenomenon of diffraction. So by using this experiment, he confirmed the existence of matter waves. Option A is the correct answer. Question number 6 is told that according to Einstein's photoelectric equation, the graph of kinetic energy of the photoelectron emitted from the matter versus the frequency of the incident radiation. So we know that kinetic energy, that is equal to h nu minus the work function phi naught. So the kinetic energy versus the frequency graph, that will be somewhat like this, will be like this, and this will be phi naught minus phi naught. So the slope, the kinetic energy of the photoelectron emitted from the metal versus the frequency of the incident radiation gives a straight line graph whose slope depends on the intensity, depends on the nature of the material. So here the slope is nothing but the Planck's constant, which, so it is same for all metals and independent of the intensity of incident radiation. So option C is the correct answer. And in question number 7 is told a photoelectric threshold wavelength for silver photoelectric threshold wavelength for silver is lambda naught. The energy of the electron ejected the energy of the electron ejected from the surface of the silver by an incident wavelength lambda will be lambda is less than lambda. Photoelectric threshold wavelength for silver is lambda naught. The energy of the electron ejected the surface of the silver by an incident wavelength lambda. So the kinetic energy that will be equal to hc by lambda minus hc by lambda naught. So that will be equal to hc into 1 by lambda minus 1 by lambda naught. That will be equal to hc into lambda naught minus lambda by lambda naught. So option D is the correct answer. Then question number 8. So an electron of mass me and a proton of mass mp are moving with the same speed. Moving with the same speed. Mass and they are moving with the same speed v, suppose. Then the ratio of the de Broglie wavelengths will be so lambda e by lambda p. So that lambda e will be h by me into v divided by h by mp into v. So this will be equal to mp by mass of proton by mass of the electron. This is obviously more than 1, and mass of the proton is equal to 1.67 into 10 power minus 27 gram divided by this is mass of electron is 9.11 into 10 power minus 31 kg. So it is minus 27 kg. This is minus 30. So this is approximately 1836. Option B is the correct answer. So how we got 1836? That is like 1.67 into 10 power minus 27 right, plus 31 divided by 9.11. And 9.11 is approximately, okay, so 1.67 by 9, that is so this is like 1.836. 1.67 by 9.11, it is approximately 1.836 into 10 power is 4. You know, this is 0.1836. 0.1836 into 10 power, this is 4. So this will be approximately 1836. Then in question number 9, it is told that n photons of wavelength lambda are absorbed by a black body. This is a black body which absorbs n number of photons in it, n photons each, and they are having wavelength lambda. And a black body of mass m, its mass is m. The momentum gained by the body is the momentum that is equals to absorbed, so it is completely absorbed, so it is E is equal to U by C. The energy of the photons divided by C. This is nh n into the number of photons into the energy of each photon, that is hc by lambda divided by c. C and c will cancel, so this is nh by lambda. H by lambda. So option D is the correct answer. Then question number 10, it is told a proton is there, and alpha particle are accelerated under the same potential difference. So the potential difference applied is the same, so they are accelerated. The ratio of the de Broglie wavelengths of the proton and the alpha particle is, the ratio of the de Broglie wavelengths of the proton and the alpha particle is, the wavelength of the proton accelerated under the same potential difference. So the charge of a proton is E and its mass is suppose m. Then the charge of an alpha particle is 2e, since it is helium nucleus He24. So its charge is 2e and its mass is 4m. So when it is accelerated by the same potential difference, then the kinetic energy gain will be the same. Okay, so the kinetic energy gained by the proton, that will be equal to charge into the potential difference, that is EV. And the kinetic energy gained by the alpha particle, that will be equal to the charge times the potential difference, that is 2E. Now, so the de Broglie wavelength of proton by the de Broglie wavelength of the alpha particle, that will be equal to h by square root of 2m into kinetic energy. Since you know that lambda is equal to h by p, but p is equal to root over 2 into mass into kinetic energy. 2 into mass of proton into kinetic energy of proton divided by h by root over 2 into mass of alpha particle into kinetic energy gained by alpha particle. So h and root 2, that will cancel. That will be root over m alpha into k alpha divided by mp into kp. Therefore, lambda p by lambda alpha, that will be equal to root over mass of alpha particle is 4m and kinetic energy is 2ev divided by mass of proton is m. Kinetic energy of proton is e. So this will be equal to root over 8, equal to 2 root 2. Root over 8. So option A is the correct answer. Then in question number 11, it is told the additional energy that should be given to an electron, the additional energy that should be given to it, so given to an electron to reduce its de Broglie wavelength from 1 nanometer to 0.5 nanometer is. So its initial wavelength is, suppose its initial de Broglie wavelength is 1 nanometer and final de Broglie wavelength is 0.5 nanometer. So how much additional energy should be given? Let that additional energy be delta E. So let delta E be the required additional energy, to decrease its de Broglie wavelength. So then, therefore, you know that lambda will be equal to h by square root of 2m into kinetic energy. Let that energy, I can write it as delta k. Means additional kinetic energy should be applied to it. So now, therefore, lambda initial, that is equal to 1 by root over 2m into kinetic energy initial. where m is the mass of the electron. M is the mass of the electron. K is the kinetic energy of the electron, and lambda final is also h by 2m into kinetic energy final. So if you take the ratio in lambda f by lambda I, that will be equal to h by root over 2m kf divided by h by root over 2m ki. So this will be equal to root over ki by kf. So lambda final is 0.5 nanometer divided by lambda initial is 1 nanometer, that is equal to root over ki by kf. So therefore ki by kf, that is equal to, so this will be half, so half square, that is 1 by 4. So the final kinetic energy, that is equal to 4 times of the initial kinetic energy. So therefore the additional kinetic energy, that is delta K, that will be equal to final kinetic energy minus initial kinetic energy, that is equal to 3 times the initial kinetic energy. So 3 times of the initial kinetic energy should be supplied to the electron so as to reduce its de Broglie wavelength from 1 nanometer to 0.5 nanometer. So option B is the correct answer. Option B is the correct answer. Then in question number 12, it is told the maximum velocity of the photoelectron, that is emitted by a metal. It will emit a photoelectron. And the maximum velocity of that is 1.8 into 10 power 6 per second. Take the value of specific charge of the electron, means charge to mass ratio of the electron, that is equal to 1.8 into 10 power 11 coulomb per kg. Then the stopping potential in volts is how much? So we know that the stopping potential means E into V S, that is equals to maximum kinetic energy, that is equal to half m V max square. Let us call it small. So Vs is the stopping potential. So stopping potential, how to find, is equal to m V max square divided by 2, where E is the charge of the electron. So this I can write it as V max square divided by 2 into E by m. So this will be equal to V max 1.8 into 10 power 6 whole square divided by 2 into E by m, that is 1.8 into 10 power 11. This will be equal to 1.8 into 1.8 into 10 power 26 at 12 divided by 2 into 1.8 into 10 power 11. So this will be equal to 1.8 will cancel, so 2 9s 18, 0.9 into 10, that is 9. So the stopping potential is 9 volts. Option C is the correct answer. Then in question number 13, it is told that lambda 1 and lambda 2 are used to illuminate the slits. Lambda 1 and lambda 2 are used to illuminate the slits. Then beta 1 and beta 2 are the corresponding fringe widths. The wavelength lambda 1 can produce photoelectric effect when incident on a metal, but the lambda 2 cannot produce photoelectric effect. The correct relation in between beta 1 and beta 2 is. So we know that the fringe weight in a Young's double slit experiment, that is beta that is given as lambda d by d, where d is the distance in between the plane of the slits and the screen, d is the width of, and d is the separation in between the two slits. The distance in between the two slits is d. So therefore the fringe width beta that is proportional to the wavelength lambda. So now means that beta 1 is also equal to lambda 1 d by d, and beta 2 is also equal to lambda 2 d by d. So now wavelength lambda 2 cannot produce photoelectric effect and lambda 1 can produce photoelectric effect. It means that hc by lambda 1, this energy is obviously more than this energy, hc by lambda 2. And the thing is that hc by lambda 1, since lambda 1 can produce photoelectric effect, so this is more than the work function of that work function. So it means the phi naught, which is the work function of that metal on which the photoelectric effect will happen. This is the work function of that metal on which the photoelectric effect will happen, and this is greater than hc by lambda 2. But since why this wavelength cannot produce photoelectric effect, so this energy is less than the work function. So therefore 1 by lambda 1 is more than 1 by lambda 2, means that lambda 1 is less than lambda 2. So it means that beta 1 is less than beta 2. So option A is the correct answer. And in question number 14 it is told that what is the de Broglie wavelength of the electron accelerated through a potential difference of 100 volts. So the de Broglie wavelength of an electron that is given as h by square root of 2 into mass of electron into e into the voltage through which it is being accelerated. So this will be equal to h by square root of 2 and e. So this wavelength that is given as, so this values h by square root of 2 mass of electron into the charge of the electron, this is approximately equal to 12.27 angstrom into square root of volts. Angstrom into square root of volts. So this I can write 1, it is 12.27 divided by root v angstrom, where v is the potential difference in volts, where v is the potential difference in volts through which the electron has been accelerated. This is the potential difference, in volts, through which the electron has been accelerated. So therefore the wavelength, de Broglie wavelength of the electron, that will be equal to 12.27 divided by root over 100 much angstrom. So that will be equal to 1.227 angstrom. Option D is the correct answer. Then in question number 15, it is told the maximum kinetic energy of the photoelectrons depends only on the maximum kinetic energy of the photoelectron, that is equals to h nu minus the work function. So it depends only on the frequency of the incident incident wave, it only depends on the frequency of the incident electromagnetic wave. Option D is the correct answer. Then in question number 16 it is told, find the de Broglie wavelength of an electron with kinetic energy 120 electron volt. Kinetic energy is 120 electron volt. We know that lambda is the de Broglie wavelength is given as h by square root of 2 me into kinetic energy. 2 into mass of electron into kinetic energy. So the kinetic energy is 120 electron volts. So this I can write h by root over 2 into mass of electron into 120 electron volt. 120 into 10 power 120 into 1.6 into 10 power minus 19 this much joule. One electron volt is equal to 1.6 into 10 power minus 19 joule. So now the thing is, the value of h by root over 2 into mass of electron, h is the Planck's constant, into mass of electron, which is 9.1 to 10 power minus 31, into 1.6 into 10 power minus 19, which is actually equal to root over, means h by root over 2 into mass of electron into the charge of electron. That is approximately equal to 12.27 angstrom into root voltage into root volts. So therefore the wavelength of the electron, that will be given as, that is h by root over 2 me into e into, this is 1 by root over 120. This much angstrom. So this will be equal to, this is 12.27 by root over 120, this much angstrom. So this is into 10 power minus 10 meter. Now this is approximate wavelength of the electron, that is equal to, plus that, so that I can write 0.1227 into 10 power minus 12 divided by root over 120, that is 4 3s are 12. So 120 is approximately 121 I can take, so that is approximately 11. So this much meter, so this is approximately 11 ones are 11, 11 ones are 11, 11, 17, 11 twos are approximately 22. So this much picometer I can say. Since 1 picometer is 10 power minus 12 meter. So approximately the wavelength, the de Broglie wavelength of the electron is 112 picometer. Option D is the correct answer. Option D is the correct answer. So then question number 17 is told, light of two different frequencies, nu1 and nu2, whose photons have energies 1 electron volt and 2.5 electron volt respectively, successively illuminate a metallic surface whose work function is 0.5 electron volt. Ratio of maximum speeds of emitted electrons will be. So here h nu1, that is the energy of the first photon, that is 1 electron volt. h nu2, that is the energy of the second photon, that is 2.5 electron volt. So therefore the kinetic energy, that is half m into V max square, maximum speeds, half m into V max square, V1 square divided by half m into v2 square so this will be equal to h nu 1 minus phi naught divided by this is h nu 2 minus phi naught ratio of the maximum speeds. So this is the ratio of their kinetic energy. So half m will cancel, where m is the mass of the photoelectron. So therefore v1 by v2 whole square. This is the ratio of their maximum speeds, that is equal square of that is equal to h nu 1, that is 1 electron volt minus 2.5 electron volt divided by 2.5 electron volt minus 2.5 electron volt v1 by v2 whole square, that is equal to 0.5 by 2. So that is 1 by 4. So therefore v1 by v2 that is equal to 1 by 2. Therefore the ratio is 1:2. And D is the correct answer. Then the variation of photo current with collector potential for different frequencies of incident radiation nu1, nu2 and nu3 is shown in the figure. Variation of photocurrent collector potential. Then so here the stopping potential is different. So here what is happening? The stopping potential for the third case is more than the stopping potential for the second case, which is more than stopping potential for the first case. So stopping potential V naught, that is equals to that is h nu by E minus phi naught by E. So now when the frequency is higher, so phi naught by E that is constant. So when the frequency is higher, then the stopping potential is also higher. So therefore the stopping potential for the third frequency is the highest. So the third frequency in the third case is also the highest. So nu3 is greater than nu2 is greater than nu1. Nu1 is less than nu2. So option C is the correct answer. Then in question number 19 it is told that it is told the de Broglie wavelength of an electron accelerated to a potential of 400 volts is approximately. So the de Broglie wavelength of the electron is given as h by root over 2m mass of electron into E into V, where V is the potential difference through which the electron has been accelerated. So now lambda by E, that is this I can write h by root over 2m into E divided by root over 1. So this value is approximately 12.27 angstrom volt square root of volts. So this divided by root B angstrom event. So therefore here V is equal to 400 volts. So therefore here the de Broglie wavelength will be 12.27 by root over 400 angstrom, that is 10 power minus 10 meter. So this I can write 1.227 divided by 20 10 power minus 9 meter. So this is equal to so this is 0.1227 divided by 2 nanometer. Since why 1 nanometer, that is equal to 10 power minus 9 meter. So this would be approximately 0.26 12 to 1 is 2, 3 is 6, 5 is 10. So approximately 0.06 nanometer. Option D is the correct answer. Then in question number 20, it is told a particle is dropped from a height. A particle is dropped from a height h. Then the de Broglie wavelength of the particle depends on the height as. So let's suppose its mass is m. De Broglie wavelength depends on the height as. So then kinetic energy at this point, kinetic energy when it will reach, that will be equal to half mv square, that is equal to mgh. Therefore, the de Broglie wavelength of this particle will be equal to h by root over 2m into kinetic energy. So that is h by root over 2m into mgh. Therefore, I can say this is some constant h by m root 2g into h power minus half. Therefore, the wavelength, de Broglie wavelength, it depends on, it is proportional to h power minus half. So option B is the correct answer. Then in question number 21, it is told from the following graph of photocurrent against collector potential for two different intensities of light I1 and I2, one can conclude. So when the intensity is higher, then the photocurrent is also higher. If it is higher, then the photocurrent is also higher. So I2 is greater than I1. So here the option is not there. So the option C was, so here actually the option C was 21. The option C was I. Option C was I1 is less than I2. Option D was comparison is not possible. Comparison is not possible. So here option C will be the correct answer. I2 is more than, since more photocurrent means more intensity. Then in question number 22, it is told the number of photons falling per second. Number of photons falling per second on a completely darkened plate. So we have a completely darkened plate. So it is a so purely darkened plate means here there is complete absorption. There is complete absorption and there is no reflection. So all the photons are being absorbed. Let's say n is the number of photons falling per second. N photons are being absorbed by this darkened plate per second. Then a force is produced on it. The force produced is 6.62 into 10 power minus 5 Newton. If the wavelength of the light falling, wavelength of the light that is falling, that is lambda, that is 5 into 10 power minus 7 meter, then n is equal to how much? And we have to take the Planck's constant as 6.62 into 10 power minus 34 joule second. So now the momentum, the change in momentum for complete absorption, the change in momentum of the plate for complete absorption, that is given as U by C, where U is the energy of the photons per second. So this is the change in momentum per second, that is equal to the force actually, that is E by T. So that is also U by C into 1 by T. So that is the force. So the number of photons which is falling per second, I can write that is n n into, that is hc by lambda. That hc by lambda is the energy per photon. The energy of a single photon, that is hc by lambda, that divided by c. So that is nh by lambda. nh by lambda is equal to the force. Therefore, the number of photons that is falling per second, so that n will be equal to n h by lambda, that is equal to f. So therefore, n will be equal to f lambda by h. F lambda by h. So f is 6.62 into 10 power minus 5 into lambda, that is 5 into 10 power minus 7, divided by h, that is 6.62 into 10 power minus 34. 6.62 will cancel out, so this is 5 into 10 power 34 minus 12. So this is 5 into 10 power 22. So these many photons are falling per second. So the blanks, it should be 5. Option D is the correct answer. Then in question number 23, it is told the maximum kinetic energy of the emitted photoelectrons, that depends on the frequency of the incident radiation, since it is h nu minus the work function. So it depends on the frequency of the incident radiation. So option D is the correct answer. Okay. So here we shall end the first part of this video on the chapter on dual nature of matter and radiation. So if you have any doubts, then write that in the comments section. And please install our Sapience education application, where we shall upload some important homework questions on the previous year KCET exam, and which shall be helpful for your KCET exam. Thank you everyone. Bye.